Hi, I'm Seth. In this video, I'm going to help you build more intuition for the relationship between test length and reliability as described by the Spearman-Brown prophecy formula, but I'm going to do it in a strange way. Following a brief introduction, I'm hardly going to mention the Spearman-Brown formula at all. Instead, I'm going to spend the entire video helping you build intuition around a single scenario where you go from having one test item to having two test items. In other words, the simplest case of doubling the number of items from one to two. I believe that if you grasp that scenario at an intuitive level, you'll be able to extrapolate that to any other scenario, whether that means quadrupling the number of test items, dividing the number of items by 10, or whatever. The same concept will apply, and you'll be able to understand how reliability is affected. So to do this, I'm first going to briefly review the Spearman-Brown formula. After that, I'm going to show you why the formula is true using three different kinds of arguments. First, empirical demonstrations, then a mathematical explanation, and finally a geometric explanation. More specifically, for those of you for whom seeing is believing, I'm going to run some simulations in R to show what happens. Then for those of you more mathematically or formulaically inclined, I'm going to derive the results of the Spearman-Brown formula using the variance sum law. And then I'm going to show you why the formula is correct using Pythagorean addition, which, as I'm saying it, I'm realizing is the nerdiest statement I've ever said. Anyway, hopefully at least one or maybe all three of the following explanations will help you understand the connection between test length and reliability at a more intuitive gut level. Now, when I say the Spearman-Brown formula is correct or true, you're going to have to imagine a big asterisk and then a footnote at the bottom of the page that says, if we accept the assumptions of classical test theory, which is not the focus of this video. One other thing, if it hasn't already become clear, this is a video for people who really want to go down the rabbit hole and understand test length and reliability at a deep level. And if that's you, then stick with me because I promise it'll pay off by the end. But on that note, here's a brief word of warning. It's going to be helpful if you come into this with at least a basic understanding of concepts like classical test theory, reliability, and the Spearman-Brown formula even if you don't have a very strong intuition for how they work yet. My first two videos on these topics will give you the baseline knowledge you need to understand everything in this video. It'll also help if you have at least a rudimentary understanding of concepts like variance, covariance, and standard deviation. I will explain all these things, but I'll be moving pretty quickly at some points. So, okay, first I'm going to briefly review the Spearman-Brown formula, which is the motivation for this video. This formula estimates how the reliability of a test would change if we changed the length of the test, whether that means number of items, number of raters, or whatever number of measurements. RXX, right here, this is our original reliability estimate. N is our scaling factor. So for example, if we're quadrupling the number of items, that means N equals 4. And then RXX with an asterisk after it is what we would predict our reliability estimate would become after we change the test length. By the way, this formula is assuming that whatever items we add or drop are comparable to the rest of the items. In essence, the numerator scales the reliability estimate based on the change in test length, but doing so knocks the estimate off the normal 0 to 1 scale. So then the denominator yanks that result back onto a 0 to 1 scale. The details of how this works are spelled out in my video titled The Spearman-Brown Prophecy Formula Explained. Here's a visualization of how this works. Reliability is defined as the proportion of variance in a distribution of scores that is attributable to true score. So here, where the reliability is 0.5, there are equal parts true score variance and error variance. It's a 1-to-1 ratio. Now, what would happen if we doubled the test length, meaning we had twice as many items? The answer is that the average amount of error variance would be cut in half. Equivalently, you could think of it as the relative amount of true score variance doubling. I'll show you how those are really the same thing later on. Now we have a 2-to-1 ratio of true score variance to error variance. That means 2/3 of total variance is attributable to true score, and 2 divided by 3 is about 0.67. So that's what our new reliability estimate would become. Here we can see that that's exactly what the Spearman-Brown prophecy formula shows when we plug in the relevant numbers. So this formula is just capturing that same idea that I showed you with that visualization. Again, watch the video on this formula if you want to understand how it works better. Now, here's a visualization I showed you in the original video. This was the part that I thought was trickiest, and based on feedback from viewers, many people did find this confusing. Classical test theory states that a given score, represented by X, is usually not exactly the same as the person's true score, represented by T. There's usually some amount of error, represented by E. So you can see in this visualization that there is a true score, which is a bit different from the observed score, and the difference between them is error. Additionally, classical test theory assumes that error is randomly distributed about the true score. In other words, the true score is the mean, the center of a distribution of random error. It's most likely the observed score is relatively close to the true score, so that's small error, and it's less likely that the observed score is relatively far out in the tails of the distribution, which would mean large error. So when we only have one item, that means we have one error. And that error could happen to land anywhere in this distribution on a given measurement of this attribute. The height of the curve represents how likely the error is to land in that particular location. Again, nearer to the true score is most likely, and out in the tails is least likely. Now, when we double the test length from 1 to 2 items, that means we have 2 scores, which we average. The average, or mean, of the 2 scores is the midpoint between them. As we look at a few examples, I think it'll be clear to you that the mean of the 2 scores has to be closer to the true score, on average, than the individual scores themselves will be. So the individual scores are varying as much as they usually would, but the averages of pairs of scores varies less. The fact that they are between any 2 pairs of scores means they've got to be closer to the center of the distribution, on average. This explains why doubling the test length cuts the error variance in half. When we calculate the average, we're dividing by 2, and so that divides the variability, specifically the variance, by 2 as well. That may seem intuitive to some people, but it's not intuitive to everyone. And that's the reason for this video, the rest of which will focus on building intuition for how and why that works. Now, quick sidebar. If you're one of those people for whom all of this already makes a lot of sense, then I've got a bonus challenge for you. Here it is. If we double the number of test items, then on average, how much closer must each observed score move toward its respective true score? Or, put another way, by what factor must the average error shrink? And it doesn't matter if you're thinking the average error as being the standard deviation or the mean absolute deviation. The answer is going to be the same. Now, before getting into the 3 explanations, we should get clear on what the relevant terms mean. Starting with the variance. You might see this represented as sigma squared or S squared if it's based on sample data. In this video, I'm going to use the notation for population variance, so sigma squared, because that's going to simplify the formulas that we deal with. All right, what is it? Well, variance is the average squared deviation from the mean. In this context, when I say average, I'm talking about the arithmetic mean. So add things up and divide by the number of them. A deviation from the mean is just the difference between a given score and the mean of that distribution. So we're taking each deviation from the mean, then we're squaring it, and then we're averaging all of those. So the variance is the average size of a squared deviation. Now, how can we think about a squared deviation? Let's look at an example. What is the difference or the deviation between 5 and 3.5? It's a deviation of 1.5, which you can see represented here on the number lines. Just subtract one from the other. So what then is the squared deviation of 5 from 3.5? Well, it's just 1.5 squared, which is 2.25. And I like to visualize squared deviations using actual squares where each side has a length that's equal to the deviation itself. So here you can see that a square with a side length of 1.5 has an area of 2.25 square units. But it's still weird to think about squared units, which is why we'll often take the square root of the variance to get what is called the standard deviation. It's just that. This is the formula for the variance, and we take the square root of it to get the standard deviation. So it's taking the average squared deviation and then converting it into unsquared units. So the standard deviation is a type of average deviation, so it's a number that represents about how far a given score is from the mean on average. Now, since the variance is represented by sigma squared, and we're taking the square root of that to get the standard deviation, the notation for standard deviation will just be lowercase sigma. Another type of average deviation is the mean absolute deviation. And the name says it all. It's the average absolute deviation from the mean. So again, we take all of the deviations, but rather than squaring them, we now just take the absolute value of them. So for example, the absolute value of -3 is just 3. And then we add all those up and divide by the number. So we're just averaging. Now, the mean absolute deviation may seem more intuitive and useful because it doesn't involve this convoluted process of squaring the deviations and then eventually taking the square root, but it's actually less versatile than the standard deviation. So we typically rely more on the standard deviation. Regardless, we're going to see how each of these is affected when we double the test length. Also relevant is the covariance. This is the average product of deviations for two variables. So for a given person or case, we take their deviation from the mean for one variable, and then we multiply it times their deviation from the mean on another variable. And then we average these products, add up all of those products, and divide by the number of them. If the covariance is a positive number, that means the two variables are positively related, and so they will be positively correlated as well. If the covariance is 0, that means the two variables are unrelated. And if the covariance is negative, that means the two variables are negatively related. So what is the link between covariance and correlation? It's two different ways of expressing the same thing. If you standardize the covariance, it becomes the correlation, which might be more familiar to some people. Something you might notice is that the variance and covariance are doing very similar things. In fact, the variance is a particular case of the covariance where you're multiplying each deviation times itself rather than the corresponding deviation for a different variable. So the variance tells us about how much a single distribution of scores tends to vary alone, and the covariance tells us about how much two different distributions of scores tend to vary together. In other words, to what extent do they covary? Another way to think of it is that the variance is the average squared deviation. Covariance then is the average shared deviation. Whereas multiplying a deviation times itself is going to form a square. Multiplying two different deviations together will form a rectangle. I'll go into the implications of that in another video. Okay, that should be enough background information. First, I'm going to empirically demonstrate that doubling the test length cuts error variance in half. I'm going to do this by drawing many scores from a distribution and then calculating the variance. Then I'm going to draw many pairs of scores from the same distribution and calculate the variance of that distribution. Spoiler alert, in the latter case, the variance is going to be approximately half of what it is in the former case. Something that might help build your intuition is to realize that this property is not unique to a normal distribution of random error. In fact, for almost any distribution you're likely to be working with in the social sciences, this property is going to apply, and I'll briefly show you each of these. But first, I'm going to walk through what I consider to be the clearest and most intuitive case, which is based on Bernoulli trials. A Bernoulli trial is a random experiment where you have two possible outcomes. You could think of those as yes and no, success and failure, this or that. We usually represent failure with 0 and success with 1, but for this example, I've rescaled the values to -1 and +1 because it'll make the intuition clearer for what I'm about to show you. So here's an empirical distribution of 10,000 scores that I drew using R, where the probability of one versus the other is 0.5, so 50-50 odds. Theoretically, we're expecting half to land on -1 and half to land on +1. You can see it's not exactly 50-50. The bars aren't exactly the same height, but it's close. And the more draws that we take, the more that ratio would converge on 50% in one bucket and 50% in the other. So think for a moment, what would be the approximate variance of this distribution of 10,000 scores? As a hint, you should be able to solve this in your head, and you might not even need to do any calculations at all to know the answer. By the way, note that for the following explanation, I'm going to be a bit loose with my calculations. I'm going to use approximations rather than precise values because I want you to focus on intuition rather than tiny differences due to rounding. Okay, so what answer did you come to? The correct answer is that the variance of this distribution would be about 1. In actuality, due to randomness, it might be 0.99 something or maybe 1.00 something, but it's very close to 1. Why is that? Well, the mean of this distribution is about 0. Around half the values are -1 and around half the values are +1. So the average should be halfway between those two values, which is 0. And remember that the variance is the average squared deviation from the mean. So we're going to take these scores as deviations from 0, then square them, and then average them. Now, about half the deviations are -1. When we square that, we get +1. And the other half of the deviations are +1. When we square that, we also get +1. So if all the squared deviations are approximately 1, then the average squared deviation is approximately 1. To put it simply, every deviation has a magnitude of about 1, so when you square them, they remain values of 1. Therefore, the average squared deviation is 1. Again, because these bars are not exactly the same height, the mean isn't exactly 0, and the variance isn't exactly 1, but it's something very close to those values. Okay, so here's where the core intuition lies. The distribution on the left is what I got from drawing 10,000 values that could either be -1 or +1 with 50% probability of either. Imagine what the distribution would look like if I drew 10,000 pairs of values and then averaged them. Take a moment and see if you can visualize what that's going to look like. As a hint, it might help to think about what the possible pairings could be. Okay, so you might draw two values of -1, or you might draw two values of +1, or you could end up with one of each, -1 then +1, or +1 and then -1. Okay, here's what it would look like. About 1/4 of the time, we'd get -1 for both draws, so that average would be -1. About 1/4 of the time, we'd get +1 for both draws, so that average would be +1. And the other half of the time, we'd get a mix, either a negative then a positive, or a positive then a negative, and the average of those is 0. Now, I really recommend that you pay attention here because I think this is the core visualization that makes everything click. When we draw two scores from a distribution and average them, the values are able to cancel out to some extent. And so the weight of the distribution starts sliding toward the middle. In this case, about half the weight of the distribution has slid into 0. -1 and +1 cancel out to 0 in about half the cases. So the mean of this distribution is something very close to 0. Consequently, about 1/4 of the deviations around -1 and about 1/4 of the deviations around +1. Square both of those and you get +1. And then the other half of the deviations are around 0. Square that and you get 0. So if half the squared deviations are about 1 and half the squared deviations are about 0, then the average squared deviation is halfway between those values. Halfway between 0 and 1 is 0.5. Again, these proportions aren't exactly 25% and 50%, so the mean is something close to 0 and the variance is something close to 0.5. To me, This is a very clear intuition for why averaging pairs of scores will result in half as much variance as simply drawing single scores. Originally, the average deviation was 1, and then here, half the weight goes to 0 because two scores can cancel out. So the average squared deviation drops to 1/2, or 0.5. For me, that is the core intuition of this video. I'll show you more simulations, but only for the purpose of generalizing this core concept to other distributions. For example, here's what we'd get if we drew 10,000 sets of 4 scores that are either -1 or +1, and we average them. If we calculate the variance, it's going to be approximately 0.25. So when we go from 2 to 4 draws, the variance is halved from 0.5 to 0.25. Again, if we double the number of draws from 4 to 8, the variance of the resulting distribution is halved again, dropping from 0.25 to 0.125, like dropping from 1/4 to 1/8. Now, it's probably less intuitively clear in these examples, but we're just scaling up the same concept from the 1 and 2 score scenarios. You might also notice that as we add more and more draws, the resulting distribution starts to look more and more like a normal distribution. This hints at how all the common distributions we deal with in social sciences are actually connected to one another. I'm not going to go into it, but it might help a bit with understanding why they all share these properties I'm demonstrating. Okay, now I'm going to briefly run some live simulations where I'll show you what a particular distribution theoretically looks like, and then I'll first draw 10,000 individual scores, then 10,000 pairs of scores, which get averaged. In each case, you'll see how the variability of the resulting distribution of those draws shrinks when we're dealing with the midpoint between two scores, and how the variance of that distribution is approximately half as much as that of the first distribution. I'm keeping most of the code hidden because I don't want you worrying about how I'm doing this. I just want you to focus on the visualizations. So for all these distributions, worry less about what the distribution means and where you might see it in your work or studies, and focus more on just comparing pairs of distributions. So here's what's called the probability mass function for a binomial distribution with one draw, which is a Bernoulli distribution, but don't worry about that. This tells us how likely these two possible outcomes are. Oh, here I've scaled it as 0 and 1 rather than -1 and +1, but it's the same thing. So again, this is an example of where the probability of each outcome is 0.5, as you can see. So this is theoretically what we would expect. But now let's simulate some data. As I showed you before, we can compare 10,000 draws to the average of 10,000 pairs of draws. So here is the first. I drew 10,000 values. The variance of this empirical distribution is 0.9999, so about 1. So what we're expecting now when we draw 10,000 pairs from this distribution and average them is, yep, that same distribution we saw before. You can see the variance drops to about 0.5, so it's half of what it was in the first case. And then, like I showed you before, we could then double to 4 draws. The variance drops to 0.246, or about 1/4. And then with 5 draws, it drops to about 1.23, which is around 1/8. Okay, so now let's generalize this to a few other distributions. This is called the Poisson distribution, where lambda equals 3. Don't worry about what lambda means if you don't already know. Let's see what happens when we draw 10,000 values from this distribution. Okay, so it resembles the theoretical distribution it was drawn from, and the variance, as you can see, is about 3. So when we draw 10,000 pairs of values and average them, we're expecting the resulting distribution to be less spread out, and we're expecting that distribution's variance to be about 1.5. Okay, so it is less spread out, and the variance is about 1.5. So the variance is about half as much for this distribution as for this. Okay, what about an exponential distribution? That might look something like this. Now, this is actually called a probability density function. It's like a probability mass function, but for continuous data rather than discrete data. The curve represents the same thing as before. It's the likelihood of a given score being randomly drawn from this distribution. So let's draw 10,000 individual scores and then 10,000 pairs of scores. So when we draw 10,000 individual scores, the variance is about 1. When we draw 10,000 pairs of scores on average, you can see there's less spread, and then the variance drops from 1 to about 0.5. So that's about half. What about a uniform distribution? This is a distribution where every value is equally likely. Well, when we draw 10,000 individual scores, we end up with a distribution whose variance is 6.88. We're theoretically expecting that to be like 6.75, I think. Now, when we draw 10,000 pairs of scores in average, you can see the shape is changing, the spread is reducing, and the variance has dropped to 3.4, which is about half. I think we'd expect 3.375. I think that's half of 6.75. All right, let's keep going. What about a gamma distribution, which looks like this? Our first distribution has a variance of about 2. So we're expecting our second distribution to have a variance of about 1. Let's see what happens. Yep, the x-axis is scaled a little differently, but this is actually less spread out. And then, yeah, the variance drops to 1. Okay, and now let's take it to something that maybe more of us might be interested in, which is a normal distribution. All right, in our first set, so 10,000 individual draws, the variance is about 1. So for 10,000 pairs of draws, where we're averaging, we should come to about 0.5, which is exactly what happens. All right, so I think that does it for our empirical demonstrations of how this works. Now let's move on to the second segment, which is about mathematical or formulaic explanations. For some people, this is what's convincing, just seeing that the equations work out. So this explanation is going to be based on what's called the variance sum law. This describes what happens when we combine random variables together. Since this video focuses on a scenario where we increase from 1 to 2 items, I'm going to focus on this version of the formula, which only involves 2 variables or 2 items. What this formula says is that the variance of the sum of 2 variables, x and y, is equal to the variance of x plus the variance of y plus 2 times the covariance of the 2 variables. So that's the variance in scores on item 1 plus variance in scores on item 2 plus twice the covariance of scores on the 2 items. So this is going to tell us what the variance will become when we add 2 items together. I actually prefer an alternative version of this formula, which is below. I prefer to think of this formula as showing how the variance of a sum is just the sum of the variances, but with each being adjusted by the covariance before they get added together. I might talk more about how that makes sense in a bit, but first let's just show that this formula is correct. It's called a law because it has to be correct. It's nothing more than a rearrangement of our regular old variance formula. So variance is the average squared deviation. We can take that formula and replace x with x plus y. So it's the exact same formula, but where there was an x, I've now got x plus y. Where we did have the mean of x, we've now got the mean of x plus the mean of y. Because it's not the variance of x, it's now the variance of x plus y. So it's really just taking our plain old formula and saying, hey, I want to use the sum of these two rather than one alone, and it works. We can algebraically rearrange that formula into this color-coded version. If you are mathematically inclined and enjoy proving how different equations are algebraically equivalent, then an interesting challenge for you might be to show how the second and third equations are equivalent. But setting that aside for the purpose of this video, let's just try to make sense of what at first might seem like a confusing and long equation. It turns out that this first term is just the variance of x. It's the average squared deviation of x from its mean. And the second term is the variance of y. Same thing, but for y rather than x. And the third term is 2 times the covariance of x with y. Remember the formula for the covariance? This is it. Well, double. So when we plug a sum of two variables into our variance formula, we end up with this, which is what the variance sum law tells us. It's the variance of x plus the variance of y plus 2 times their covariance. Now, some of you might notice that this formula is equivalent to just adding up everything in the variance-covariance matrix, if you're familiar with what that is. If not, it doesn't matter right now. As I said before, the covariance is just the raw correlation. It's the unstandardized correlation. So if we express covariance in standard deviation units, it becomes the correlation coefficient. So that's a way to think about what covariance is. It's telling us about the relationship between two variables. So notice that if the covariance, or the correlation, between two variables is 0, then this formula, this term just drops out, and this formula simplifies to this. The variance of the sum is simply the sum of the variances. Just add them together. But if the covariance is positive, so they're positively correlated, then we start with the sum of individual variances, but then we're adding something positive to it. There's even more spread because scores on the items vary similarly, and so the spread is increased due to reinforcement. On the other hand, if the covariance or the correlation between the two is negative, then we're subtracting from the sum of individual variances. There's going to be less spread because scores on the items, they're covariant in opposite ways. So the spread is decreased due to cancellation. Now, let's see why this useful formula can be used to show that the relative amount of error variance is going to be cut in half when we have two items on our test rather than one. Classical test theory says that each score has a true part and an error part. It follows from this that some of the variance in a distribution of scores is due to genuine, true differences between test takers, and some of the variance is due to randomness. So the variance has, it also has a true part and an error part. By the way, this is also an application of the variance sum law. Here's an equivalent version of this formula where we have the variance of one part plus the variance of the other plus 2 times their covariance, but random error doesn't correlate with anything. So the covariance is 0 and this term drops out. That's why we're just left with variance of x equals true score variance plus error variance. Now, if we assume that two items are measuring the same attribute equally well, which classical test theory does make that assumption, then we can substitute both of these individual variances with a combination of true score variance and error variance. So this is what I just showed you on the last slide. The observed variance is a combination of true score variance and error variance, so we can replace that term. And if they're measuring the same attribute, then it's theoretically the same thing here, assuming they're both measuring that attribute equally well. And since we're looking at the covariance of what are ostensibly two versions of the same thing, we could express this as the covariance of true score plus error with true score plus error. And so this is what the formula becomes. We've got two true score variance terms, so that's 2 times the true score variance. We also have two error variance terms, so that's 2 times the error variance, and then still 2 times the covariance. It happens that we can express the covariance between two sums as the sum of covariances between each pair. So true with true plus true with error plus error with true plus the covariance of error with itself. This may seem like a lot, but it simplifies dramatically because, again, random error doesn't correlate with anything by definition. So all of these, except the first term, they're going to be equal to 0, and they just drop out of the equation. Also, the covariance of something with itself is the variance. Remember that from earlier in the video? So the covariance between true score and itself is the same thing as just the true score variance. Take a moment and think that through. Make sure that you're clear on that logic. What this means is we can substitute 2 times the true score variance for this covariance term, because that's what it simplifies to. Also, because we now have 2 times the true score variance and another set of 2 times the true score variance, we can combine those like terms and end up with 4 parts, true score variance, and 2 parts, error variance. So having 4 times as much true score variance and 2 times as much error variance means the relative amount of true score variance has doubled. Or equivalently, you could think of it as the relative amount of error variance being cut in half. That's because it's a ratio of 4 to 2, which is the same as a ratio of 2 to 1. So that is a formulaic explanation for why we end up with half as much relative error variance when we double the test length. In this case, increasing from 1 item to 2 items. Now, importantly, this is an explanation of what's happening at the level of individual items. When we have more items, we have more variance at the item level. But we actually don't have more true score variance at the level of average scores. At that level, true score variance isn't going to change, but the error variance will drop. That's how I explained it in my first video, so I'll just briefly show how those two seemingly contradictory facts are actually the same thing. So in that first video, I explained that some of the variance in a distribution of scores exists due to genuine differences between test takers. So these blue bars represent true scores. This is the mean of the observed scores. So some of the variance in the distribution is due to genuine differences between the test takers on whatever attribute is being measured by the test. Here you can see 4 different true scores for 4 different people. These are like the transcendent or quote correct scores for these 4 people. Some of the variance in this distribution, though, is also due to random error. So we've got our true score, then some amount of error, and then our observed score. So some of this variance in the distribution is due to randomness. Now think about these blue bars as representing a person's true average score. So these are the transcendent values that these 4 individuals would get for the overall test after adding up however many items and dividing by the number. If that's the case, then hopefully you can see adding more items isn't going to change the amount of variance attributable to true score. There's still just one average score per test taker, and the true score theoretically doesn't change. So at this level of analysis, there's no increase in true score variance. Rather, increasing the number of items, so basing this observed score on several different items or on more items, is causing the observed score to converge on what the true score is because those random errors cancel out. So the proportion of variance in this distribution that's attributable to random error will be decreasing. In other words, reliability will be increasing, but it's not due to a change in true score variance at the level of an average score. Specifically, at the item level, doubling test length would quadruple the true score variance, while only doubling the error variance, that's a 4 to 2 ratio, so we have twice as much true score variance relative to error variance. Whereas at the level of average scores, doubling the test length results in no change in true score variance while having the error variance. So this is going to result in twice as much relative true score variance. Okay, now it's time for the third main explanation. For this explanation, we're going to think about what happens to the standard deviation of errors when we double the number of items, and then from that we'll derive what happens to the error variance. As you can probably predict, it's going to give the same answer as our empirical and mathematical explanations gave. So we're back to the challenge I posed near the beginning of the video. By what factor is the average error decreased when we double the test length? Again, you could think of that average error as a standard deviation or mean absolute deviation. You might wonder, the variance gets cut in half. Is the standard deviation also cut in half when we double the test length? Let's check and see. We know that the error variance is reduced by a factor of 1/2. So for example, if the original error variance is 1 and we double the test length, the error variance drops to 1/2. So think about it. If the error variance is 0.5, then what would the standard deviation of error have to be? Well, the standard deviation is the square root of the variance, so it has to come out to about 0.71. In other words, the standard deviation is reduced by a factor of the square root of 1/2. Doubling the test length would convert a standard deviation of 1 into a standard deviation of about 0.71. We can formalize this. So if doubling test length has the effect of scaling the error variance by a factor of 1/2, then it must have the effect of scaling the corresponding standard deviation by a factor of the square root of 1/2. Now that may just seem trivially true by virtue of the fact that the standard deviation is the square root of the variance. But could we get there by going the other way around, by starting with the standard deviation, seeing how it is affected by doubling test length, and using that to derive what happens to the variance? And yes, we can. The key is to understand how random deviations combine. Deviations can be positive or negative, so a pair of deviations might go in the same direction or different directions. The extent to which they cancel out is going to depend on their directions and their magnitudes. Typically, random errors are not going to perfectly double up, like in this example on the left, where the combined error is twice the magnitude of a single error. But similarly, random errors typically won't perfectly cancel out either, like in the example on the right, where the combined error washes out to 0. I mean, that can happen, but what's more likely is that the combined deviation will be something in between. So you might even be expecting that combination to be something between 0 and 2 times the magnitude of a single error. So the question is, how do we do it? How do we quantify that combined error? It turns out that independent errors will combine in a nonlinear way. We can represent the idea of a typical error, a typical deviation of a score from the true score, using the standard deviation. We could also use the mean absolute deviation to represent a typical error if we wanted to, but we'll come back to that. For simplicity, let's suppose the standard deviation of that normal distribution of error around the true score is just 1. This will make the math a lot easier. So how could we geometrically represent the idea of combining random errors? One way to think about this is allowed by the fact that classical test theory assumes errors, that is, the deviations of observed scores from the true scores, are random. So one error should not be related to any other error or anything else. We can represent this idea in two-dimensional space. This may seem a little strange at first because probably you're more likely to conceptualize two scores on a test as existing on a single number line. That's not wrong necessarily, but we can also think of errors as existing in as many dimensions as we have test items. If we have two test items and therefore two random errors, we could represent that in 2 dimensions like here. If we've got 3 test items, we could represent those 3 errors in 3 dimensions. Or if we had 20 test items, we could represent those 20 errors in 20 dimensions. We're thinking of it in this way to take advantage of the fact that these errors are random and therefore unrelated to each other. They're independent of one another. Geometrically, we can represent the idea of independence or orthogonality, if you want to use a fancy word, using right angles like this. We can think of these errors as vectors. We're using the standard deviation as a typical error, and we've set that equal to 1 for simplicity. So we've got 2 vectors of length 1, and they're sitting perpendicular to each other in 2D space. With me so far? If the errors were perfectly positively correlated, meaning that they were the same thing, then the 2 vectors would lie right on top of each other, pointing in the same direction. For example, if the first error were positive 1, then the second error would also be positive 1. On the other hand, if the errors were perfectly negatively correlated, meaning they're opposites of each other, then the 2 vectors would point in exactly opposite directions. For example, if the first error were at positive 1, the second error would be at negative 1, pointing in opposite directions. But there is a 0 correlation between these 2 errors. That's a fundamental assumption of classical test theory, that random errors don't correlate with anything, including each other. So the 2 vectors are at a right angle. If you're friendly with trigonometry, you might even notice that the cosine of the angle between these 2 vectors is equal to the correlation, ranging from -1 to +1, and being 0 when the angle is 90 degrees, but that's not critical. So how can we visualize independent errors somehow combining in two-dimensional space? Well, we can add these together using vector addition. One way to think about that is to visualize the base of one vector sliding over until it rests on the tip of the other vector. This means that because these errors are unrelated, we could represent the combined error using this vector in 2D space. So now the question would be, okay, what's the magnitude of that vector, that combined error? And I think even if you're freaked out by what I'm doing with vectors in 2D space, I have a sneaking suspicion that you know how to figure out the length of that green vector. What I'm hoping you just said is use the Pythagorean theorem. That's right. This is a right triangle because the blue and red legs are forming a right angle. And that means the length of the green vector is the hypotenuse of this right triangle. So what is the relevant formula? A squared plus b squared equals c squared, right? If we're solving for c squared, which is this length, the hypotenuse, then it's going to be equal to the square root of what? 1 squared plus 1 squared. Remember that both of these typical error lengths were set to 1 for simplicity. Okay, so this method of finding the magnitude of the combined error is called Pythagorean addition, or sometimes you might hear it called addition in quadrature. It just means that because these errors are unrelated to each other, their combination can be derived using the Pythagorean theorem. And as we can see, the square root of 1 squared plus 1 squared is the square root of 2. But we're not just combining errors, we're averaging them. Remember, when we have two items, we take those two scores and average them. So this value needs to be divided by 2. Okay, well, what is the square root of 2 divided by 2? One solution is to say, oh, square root of 2 is about 1.414, so divide that by 2. But we could also take an intermediary step that might be enlightening. We could multiply the numerator and the denominator times the square root of 2. That's allowed because that's equivalent to multiplying the whole thing times 1. If you do that and you simplify, it's going to end up being 1 over the square root of 2, which I hope looks familiar to you. Once we calculate that, it's going to come out to approximately 0.71. So in our example, we set the standard deviation equal to 1. So that's going to be scaled by 1 over the square root of 2, and it becomes 0.71 approximately. More generally, whatever your standard deviation is, it's going to be scaled by that factor. So take the standard deviation divided by the square root of 2. And that's what the standard deviation becomes when you double your test length. Now, as promised, we can use this information to derive what must happen to the variance, which is defined as the standard deviation squared. It's formed by the product of the standard deviation with itself. The implication is that if we scale the standard deviation by a factor of 1 over the square root of 2, that scaling factor has to be the same, but squared. If you square that, it comes out to 1/2. Or if you want to think of it like this, your standard deviation divided by the square root of 2, square that, and you get the variance divided by 2, which is what we knew to expect from our previous explanations. Now, what about the mean absolute deviation? We considered what would happen if we thought of the typical deviation being the standard deviation, but the mean absolute deviation, that's also a legitimate way to think about the size of a typical deviation. And mercifully, there's nothing new to learn here because the exact same logic applies. We can assume a mean absolute deviation of 1 for simplicity, and we'll see that when we combine two such typical random errors, we're going to have a combined magnitude of the square root of 2. Then when we divide that by 2 to average, we get 1 divided by the square root of 2. So for a normal distribution, there is kind of a memorable relationship between the mean absolute deviation and the standard deviation, which is that the mean absolute deviation is going to be just under 4/5 of the standard deviation. Given this relationship, if there's some procedure that causes one of those two to be scaled by a factor of 1 over the square root of 2, then that procedure would have to scale the other by that exact same factor. Therefore, doubling test length reduces the mean absolute deviation to about 71% of its original size. Now, here's something cool. This application of Pythagorean addition will scale to however many items, and therefore however many errors we've got. For example, imagine we have 3 test items instead of 2 or 1. If they're all measuring the same thing, then the only reason they're not all exactly equal to the true score must be random error. And we know that random errors aren't correlated with anything, including each other. So we can set 3 vectors, all at right angles in 3-dimensional space. Again, we'll assume that our typical deviation has a magnitude of 1 for simplicity. Now, as before, we can use vector addition to see how these unrelated errors are expected to combine on average. Here's what you might visualize that as looking like. Each vector, its base moves to the tip of another vector, and you see where you end up. And so here is the combined error. Now you might notice that the length of this new green vector is equal to the diagonal of the cube formed by these 3 vectors. The diagonal of a cube with a side length of 1 is the square root of 3. Or if it's not clear why that's true, you can find the length using this formula. And you can, for however many dimensions you have, you can just keep adding the squared terms, and it will keep giving you the combined error. Again, however, the square root of 3 is the combination of 3 unrelated errors, but we're not just combining them, we're averaging them. So that's got to be divided by 3. We can solve this in the same way as our previous example. So we could find the square root of 3, then divide that by 3, or we could algebraically rearrange this into 1 over the square root of 3, which is approximately 0.58. So since we use the standard deviation being equal to 1 for simplicity, that means 1 gets scaled by a factor of 1 over the square root of 3, and it becomes approximately 0.58. Or more generally, whatever your standard deviation is, it's going to be scaled by a factor of 1 over the square root of 3. Notice that when we add more and more items, the typical size of the combined error is shrinking towards 0 due to those random errors canceling out. And as with everything else in this video, this aligns with the fact that increased test length results in higher reliability, assuming the items you are adding are comparable to the original items. Now, like before, we can use this to discover what happens to the error variance if we triple the test length. If the standard deviation was scaled by a factor of 1 over the square root of 3, then the variance is going to be scaled by the same thing, but squared. And if you square that, 1 squared is 1, square root of 3 squared is 3. So the error variance will be divided by 3. And this is going to apply regardless of whether you're adding or removing items and regardless of how many items you add or remove. Multiplying the test length times n will have the effect of scaling the variance by 1 over n and scaling the standard deviation by 1 over the square root of n. The last thing I'll do is briefly demonstrate that these principles and properties apply when we're working with an actual data set. So I'm going to switch over to Excel. So here's a fake data set with 6 scores. We've got 6 people and we've got their 6 observed scores. We're pretending that we can somehow omnipotently know what their true scores are, and then the errors are just the differences between them. So for example, Seth's observed score is 45, but the true score is 50. So that's an error of 45 minus 50 equals -5. By the way, I first saw this way of representing the core concepts of classical test theory in a book called Psychometrics and Introduction by R. Michael Furr. Okay, so for each column, you can see I've set up Excel to calculate the mean absolute deviation, the standard deviation, and the variance. Because reliability is the proportion observed score that true score accounts for, we can say 291.67 divided by 341.67, and that gives us 0.85. Now, let's suppose that n equals 2. We can predict what this reliability would become if we doubled the test length. So let's just plug in the Spearman-Brown formula real quick. 2 times that divided by 1 plus 2 minus 1 times that. I'm just using the Spearman-Brown formula that I showed you earlier. So we're predicting that doubling test length would raise the reliability to 0.92. Also, remember that I said an observed score is equal to the true score plus some amount of error. And then I also said the observed variance is equal to true score variance plus error variance. So that means if classical test theory is correct, the error part and the true score part should add up to this. And that's exactly what happens. So the error variance is 50 plus 291.67, and we get 341.67. It's the same. They add up to the whole. Now, if you're paying attention, you might realize technically it's also plus 2 times the covariance of true score with error, but in this case, that term is equal to 0 because I set it up so that the correlation between these two is 0. But that's a quick callback to the variance sum law and this core idea from classical test theory. Now, my challenge from the beginning of the video asked how much closer each observed score would need to move toward its respective true score on average if we doubled the test length. In other words, by what factor would the average error shrink by? So by what factor would these errors shrink by on average? Later in the video, I showed you that doubling test length has the effect of reducing the average error by a factor of 1 over the square root of 2, regardless of whether we are thinking of that average error as being the mean absolute deviation or the standard deviation. So if everything I've shown you is correct and all these pieces fit together in the way I've claimed that they do, then I should be able to shrink the distance between each observed score and its true score by a factor of 1 over the square root of 2, and that should have the effect of cutting the variance in half, reducing the standard deviation to about 71% of its current size, reducing the mean absolute deviation to about 71% of its size, and increasing the reliability to 0.92. So let's see, what are we expecting to happen? We said we'd expect for mean absolute deviation to be reduced by a factor of 1 over the square root of 2, so that should become about 0.471. Same thing for the standard deviation. We said we're expecting the variance to be cut in half, so that should become 25, and then we're expecting the reliability to become 0.92 approximately. Okay, so let's see if that's what happens. Over here on the right, I've got the same people again. Their true scores haven't changed, but I'm going to give them new observed scores such that the error part is reduced by a factor of 1 over the square root of 2. So in other words, I'm taking each error and I'm shrinking it. It's currently 100% of its length. I'm going to drop it to about 71% of its original length. Okay, so let's see, Seth, instead of having a score of 45, it would be his true score, which is 50, plus, we'll take this error of -5 and we're going to divide that by the square root of 2. Okay, so if you divided -5 by the square root of 2, it would become -3.54. That's what's happening right here, okay? So the deviation is shrinking. The score is sliding toward the true score. Now let's say we did that also for Soufei, and in fact we did it for everybody. Here's what happens. The mean absolute deviation becomes 4.71 as predicted. The standard deviation becomes 5 as predicted. The variance for the error variance becomes 25 as predicted. And then the reliability for this new distribution is 0.92. So what this shows is that these principles and properties I'm showing you, they really do hold with actual numbers, with actual data sets. It's not just abstract formulas. Okay, so that is probably more than you ever wanted to know about how test length is connected to true score variance and error variance, and therefore reliability. We explored empirical demonstrations, a formulaic explanation, a geometric explanation, and then I also showed how those principles apply using a small contrived data set. If you've got questions or video requests, don't hesitate to shoot me an email. Otherwise, till next time.